Okay, so let me just recall first that, so we were talking about, so this is a very important concept of a sequence, So a sequence is the formal definition is that you have a map from the natural number into R. And then we denote, so then the image of a particular natural number n, it's usually denoted like an, like this. You know, it could be some other, instead of a, it could be bn, potentially it could be another subscript, but this is like the most common thing, to denote it like this instead of like, but it really is a function. Okay, so that's a sequence, a subsequence. So a subsequence is that you have a sequence and then you have another map, but this map is not just any map from the integers to the integers. It has to be strictly increasing. And why does it have to be strictly increasing? Because we want, for the subsequence, if you think about the numbers that come out when you plug in when you're looking at the an, then you want some of those numbers to be in the subsequence, but you want the ordering to be the same. So this map, so that's why this map has to be strictly increasing, right? Can't sort of, you can't pick the several elements many times if it wasn't picked many times in the original sequence, right? So this is, a subsequence is where you have another map from the natural number to the natural number that is strictly increasing, and then you're looking at the composition of these two maps. So you're looking at, this thing here, right? And you call this here, and then that's usually denoted something like this, ANK. AN is the original sequence. K means that it's really that you take the image of K under this strictly increasing map, and then you're looking at the element in the sequence, right? So it's sort of NK is really, you should think about it as G of K. Okay, so that's what a subsequence is. And again, it's important that it's strictly increasing, because you want the elements to be in the same order than it was in the original sequence, and you don't even want things to be picked more times than it was in the original sequence. Okay. So that's so this whole concept of a sequence of subsequences is really important. Then the next really important concept is of convergence. So if you have a sequence an, then you say that it's converging to a. So a is another real number. It's not infinity, it's another real number. And so an converts to an converts to a if for all epsilon greater than 0, there exist n, an integer n, by capital N, such that if little n is bigger or equal to this capital N, then an minus a have to be less than epsilon, right? So if you are sufficiently far out in the sequence, then everything in that sequence is bunch epsilon close to a. Okay, that's what it's saying. And so as if you have a sequence, so a sequence that is not convergent is said to be divergent. Okay. And the next thing for sequences is just briefly reviewing this from last time. The indexing for sequences are the break laws, or whatever you want to call them. And so that is that if you take a sequence, if you have a sequence AN, and AN converts to A, BN converts to B, then if you form the sum of these two, AN plus BN, so this is a new sequence where the nth element is the sum of the nth element of the other two sequences, then this sequence here, Cn, also converge, and the limit here is the sum of the limits. Okay, and likewise, if you take if you're looking at if you define a sequence, so this was 1, 2 is that if you take a constant, so this is a constant, and you define Cn to be C times An, then this Cn also converge, and the limit here is just C times A. Right, that's the second one. Then there is one, I might have done it in the other order, but there's no, it's not, there's no particular order to have it in. The third one is that if you are looking at the products, so if you define a sequence that is given by the product of the two, then Cn converge also, and the limit is the product of the limits. And then the fourth rule is that if An is not equal to 0 for all n, and the limit here is also not equal to 0, then if you're looking at 1 over An, then those converge to 1 over N. Okay, so those are the four rules. You just write it as 4. And again, it's not like there's any particular convention with the ordering, and I think I might have done it. I might have exchanged the order of 1 and 2 last time. But okay, now let's see an example of how that works. So let's define a sequence. Let's define a sequence n squared plus 1, n squared plus n plus 1. Let's look at this sequence here. Right? For each n, that gives us actually a rational number, but it's only a real number. Now, in order to understand this, I can rewrite this one here as I can factor out 1 over n. Well, I can factor out n squared here, so I can write it like this. Like that, and then of course I can get rid of the n squared in both numerator and denominator. And now I can look, so you may as well think about the sequence as this thing here. So now if I defined, so now I can just look at, say, I can look at the sequence, which is 1. I can just first look at the sequence, which is 1 over n. If I'm looking at this sequence here, right? 1 over n, this here converts to 0. This is essentially just followed from the Archimedean property, right? But we've already seen this, that 1 over n converts to 0. And the same holds for 1 over n squared, right? This here also converts to 0, right? And so if you're looking at the sequence, you could even look at the sequence. Let's call this xn. This here is yn. I'm going to run out of character very quickly. Zn. This is just going to be the sequence, which is constant 1, right? Well, if it's constant 1, then obviously it's converging to 1, right? And so now I can just think about the sequence Bn to be equal to equal to z plus y, zn plus yn, right? This here is a sequence. Here is what yn is. Here's what zn is, right? So if you add these two, this is converging to 1. This is converging to 0. By the algebraic property of limits, this converges also to the sum of the limits. So this here converts to 1. Right? Now I can also define a sequence where I'm just adding zn, and then I'm adding xn, and then I'm adding yn. Right? This here converts to 1, this here to 0, this here to 0. So the sum here also converge to the sum of the limit, but the sum of the limits is 1. Now you have that 1 over c, now you have that, put it up here, and then I'll just go over here. So now you have that, that Cn converge to 1, and let's call this here C. And so in particular, I mean, all of these numbers here, these things here are all strictly positive. So each of the Cn's are strictly positive. So they're definitely not 0, right? So the Cn, so not only do they converge to 1, but the Cn's are not equal to 0. And the limit C, well, that's 1. So that's, of course, not equal to 0 either, right? So you can apply the fourth rule here. The fourth rule for the sequence, not for the sequence Cn, not the, right? So apply the fourth rule to the sequence Cn, and then you have that 1 over Cn converge to 1 over C, but C was 1, so this is 1, right? Now you can look at Bn times 1 over Cn. But Bn times 1 over Cn, right? Remember what Bn was. Here's Bn, and Bn is really the denominator up here, right? It's the denominator up here when you have divided by n squared on both sides. Well, not on both sides, but both in the top and the denominator. So Bn is the denominator, and Cn is the denominator. So Bn divided by Cn, this here is An, right? And now this here converge, that's what we saw over there, using the algebraic rule, it converts to 1. This here also converts to 1 by the algebraic rules. Number 3 of the algebraic rules is that for the product, it will also converge. So, and it converts to the product of the limits. So that's 1. And obviously, so this is like when you're looking at a sequence, it's often expressed in some form with some functions like this, and you do this reduction, and very quickly, this would be almost automatic, right? I mean, this is too easy almost, this one. I mean, this is the first time you see it, but in a couple of weeks, this will feel too easy. Then there will be something more complicated. Okay. So that's the algebraic rules for sequences. The next thing I want to talk about is I want to try to make more precise this about square. I mean, we made it pretty precise, but I want to think about, I don't have a very good eraser, unfortunately. Let me just see. This is a better one. This one here will make it very dirty. Okay, so the next thing I want to, so we did define square root of 2, and we talked about that quite extensively, how square root of 2, how it really was defined, and it was a real number, and the real number follows from that the field, the reals, is complete. Right? But we also we also sort of in the back of our mind, we had that we already sort of knew what square root of 2 were, right? Because when you think about square root of 2, I mean, at least I think about square root of 2, I think about it as 1.4. I mean, just because you can't really express it as a fraction. So you think about it as 1.414, etc. And then I don't remember the second years, third and fourth, whatever. But you know, you may remember just a few of the digits, fine. But so how do we make, so that's sort of our intuition with 1.4, with square root of 2. But how do we make this more precise, right? And so to make this more precise, we want to look at particular sequences, so what's called monotone sequences. So what is a monotone sequence? So there's 2 types of monotone sequence. There's one which is monotone increasing sequence. And then there's similarly monotone decreasing sequence. So a monotone increasing sequence, this is just means that for all n, you have that the next element is larger or equal to the previous element. That's a monotone increasing sequence, right? Some people talk about strictly monotone increasing, and then this here has to be a strict increasing. The second thing is kind of the obvious parallel to this is monotone decreasing sequences. So there's these 2 types. Okay, and this just means that the next element, so an plus 1, is less or equal to the previous one. Okay. And so now there's a theorem, and I'll prove this in just a minute, but I also want to, and I want to come back to square root of 2, and then I want to look at another classical example of a monotone sequence. So, right, so this is a monotone sequence, and now let me state the monotone convergence theorem. So suppose that, so this is the following theorem. Suppose that, and there's 2 versions of this. There's one version for monotone increasing sequence, and then there's one version for monotone decreasing sequence. I'll just state one of them because the other one is kind of obvious, parallel. So suppose that an is a monotone increasing sequence. That is bounded. Bounded, so this just means that there exists, i.e., there exists some a real number, so that, right, so you have a1, this here is that is monotone, right? This is monotone that they kind of increase. But the claim is that now all of the an is less or equal to this a. It's any monotone increasing sequence is clearly bounded from below, right? Because already the first element is a lower bound, right? So if you have a monotone increasing sequence, then that is bounded, then it's converging. And with limits, say, with limit A, where A is the sup of the ANs. So that is a monotone convergence sequence, okay? And that is the kind of main theorem about monotone convergence sequence is that if you have a monotone increasing sequence that is bounded, then it's also convergent. Right? And likewise, if you have a monotone decreasing sequence that is bounded from below, right, then it is also convergent. And so maybe I will state it, but it's just the obvious parallel. So this is part one of the monotone convergence sequence. Part two, or part B, is that if AN is a monotone decreasing sequence, then that is bounded from below, then AN is convergent with limit A, where A is now the inf of these numbers. Okay. Now, so you might say, the first thing you might say, we'll come to square root of 2 in just a minute, but you may say that this seems rather special, you know. Like if you take a random sequence, obviously it's not going to be monotone. But here's the thing, that so let AN be any bounded sequence. So bounded again means that it's bounded from above and bounded from below. So if you take any bounded sequence, then we can form two other sequences. Two other sequences. I mean, obviously we form many other, but here's two other very natural sequences. The first one I call Bn. And Bn is the sup of where you're starting at AN, and then you take the sup of all of the ones from AN and upwards in the sequence. Right? So this is one sequence. Right? We know that you know the set of ANs is bounded, right? So you can certainly take the sup and you get a real number, right? That gives you another sequence. You can also look at Cn similarly, where you take, instead of the sup, you take the inf of the same set. Like that. Right, so in particular, right, just to make sure it's totally clear, that if you were looking at, say, Bn, so what is Bn? If you're looking at, say, B3, then this is the sup where you're starting at A3, A4, right, etc. And so you see, of course, that B3 here, well, obviously B3 is bigger or equal to B2, right? Because B2 here is, sorry, it's not bigger equal to, it's lesser equal to B2. Right? Because you see in B2, the definition of B2, so let's just write B2 down. So B2 is that you take the sup here of A2 and then A3, A4, etc. Right? But you see that B2 here, it's both of them are defined to be sup, but B2 is defined as sup over a larger set, because in addition to these elements, it also includes A2, right? So clearly, B2 here is bigger or equal to B3. Right? And in fact, the same argument tells you that if you take Bn plus 1, then this is, or Bn, sorry, Bn is bigger or equal to Bn plus 1. Because this here is the sup over a larger set. It's sup over all the ones you take sup in here, plus An, right? So you have this property here, right? And so, yeah?
When you said the stat,
yeah.
The way that I was thinking about it is like, well, if you start, like if it's a monotone increasing.
Yeah, but it's monotone increasing, then this here, right, yeah, then it becomes very special. So it's if you take if the An was monotone increasing, then all of these, any element here would just be the A we talked about before. It would always be the limit. Right? So it somehow wouldn't be that interesting a sequence. It would be a constant sequence, and it would be just the limit. But nevertheless, it's a good example, you know.
But I guess that's still the inequality still holds.
Yeah, definitely, right, because it's just constant, exactly. Yeah. It's a good example, but it's just kind of almost like too simple because you get a constant sequence, right? So, okay, so we have, for the sequence that we defined, so we have again this, if you take any sequence, then you have two sequences, Bn and Cn, and Bn here is now a decreasing sequence. And instead of writing decreasing sequence, then it's much easier to write it like this. This is pretty standard. I mean, you know, it's just to, if you just look quickly at it, you know what this means. Yeah. You don't have to write it out. But let's look at Cn also. Remember that we assume that An could be any sequence, but it is supposed to be bounded, right? So this is now a monotone decreasing sequence that is bounded. So it actually has a limit, right? The Cn's, what about the Cn's? So the Cn's, well, Cn was defined to be the inf starting at An, like that, right? So it'd be starting like that, and so this means that if you take Cn plus 1, then you take the infimum, but you don't include this element, right? So it's an infimum over fewer elements, but then this here must be larger or equal, right, to that. So you see that the sequence Cn is monotone, this here is monotone increasing, again is bounded, and just copying from over there, the Bn was decreasing. Okay. This is like, I mean, it's also like, I mean, this is an important thing. It's also something that you would see in a lot of different contexts, where you define something, some sort of subthing, and then you have these properties. And so now, the thing is that if you're looking at, so a priori it might not be so clear to compare a random element in this sequence to a random element in that. But what is clear is that if you try to compare Bn with Cn, right? it's the same set. It's the same set. In one, you take the sup, the other, you take the inf. So, of course, Bn is bigger or equal to Cn. Right, so you have this, right? And so now you see that if you take like a random element here, if it was like further out, if it was if it was Cn further out, I just write it as something further out, so you're adding something else to it. So this would be like further out. We know that this sequence here, yeah, anyway, so you get, now you're getting this. Right, you're getting this here. Like that. And, right, so you have this. So what I should have done is that this sequence here, so you have, so let me rather draw it like this. So I have that so here is maybe C1, here is B1, and now the next element, the sequence Cn is increasing, and the sequence Bn is decreasing. So then, but you always have this here. So C2 have to lie to the right of this, but it has to lie to the left of B2. So you're getting this here. So you see that this is a way to kind of, this gives you a way to compare, right, that the Cn will always lie to the left of the Bns. Right? So you have, so now what we have done here is that we took any bounded sequence and we formed two monotone sequences. They are both monotone. And we have, so this means that now from the monotone convergence, and we haven't quite proven yet, but from the monotone convergence theorem, because these here are bounded, we have that Bn converging, they are going, they're going down, right? So they're converging, so one often would write it like this, more suggestively. That is converging downward to a limit B. And the Cn is converging upward to a limit C. Right? And so what you get is, because of all of these elements, all the Cn's lie to the left of the Bn's. This means that, and we'll prove this later, but it seems probably pretty obvious that the limit here, C, is less or equal to B. And this, so we'll come back to this also next time when we talked. If I have time, I'll talk a little bit about Cauchy sequence, but I won't really prove too much about it. But this here will play an important role when we prove the basic theorem about Cauchy sequences. Okay, so the takeaway here at the moment is just that so you have this concept of a monotone either increasing or decreasing sequence. If such a sequence is bounded, then it's convergent. That's a monotone convergence theorem. And again, from any sequence, any bounded sequence, you can there's a very natural monotone increasing sequence and a very natural monotone decreasing sequence. Now, let's try to prove the monotone convergence theorem, and then let's get back to how to think about square root of 2 in a more intuitive way using this. Okay, so now the proof of the monotone convergence theorem. So now let me just remind you what we have. So I'm only going to prove one of the two versions of it. where the sequence is monotone increasing, because the other one is just the proof is just the same with obvious modification. So I'm assuming, so this here is the assumption. So this is the assumption. So this is just that the next element is larger or equal to the previous one, and they're all bounded by this A. Right. Now we set little a equal to the sup of the ANs. Okay. And we want to show that AN converts to A. Now to do that, what we need this stuff about that for a given epsilon, there exists a capital N. Okay. So now let me first make the observation that the sup, right? So A here, since A here is the sup, it is right. So remember that the sup of a set is the smallest upper bound, right? So, but since it is, so it's so A is in particular an upper bound. So you have that AN is less than A for all N. Since A is an upper bound. It's actually the smallest upper bound, but for this you just need it's an upper bound. Okay. So I'm going to look at I'm going to look at A minus AN. And what I want to prove is that for a given epsilon, if I'm sufficiently far out, if I'm bigger than some capital, if little n is bigger than some capital N, then this here is less than epsilon, right? That's what I want to prove. But this thing here, you see, this here, I don't need the absolute value, because I already know that this is bigger than that. So I don't need the absolute value. So I can just, so this is what I want to prove. That I want to prove that for given epsilon greater than 0, there exist. Sorry, maybe let me just write it a little larger here. So what I want to prove is that given epsilon greater than 0, there exists a capital N such that if little n is bigger or equal to this capital N, then A minus AN, which I know is positive, I just need to prove that this is less than epsilon. Okay. So now how do we do that? Well, I know, so at the moment I've just used that A was an upper bound. Now I'm going to use that it's the least upper bound. So since A is the least upper bound, then A minus epsilon is not an upper bound. Right? A minus epsilon is not an upper bound. So this means that there must exist. So there exists capital N so that AN is bigger or equal. So A capital N, just this one here, is bigger than A minus epsilon, right? Because otherwise it would have been an upper bound. Right, it's actually strictly, but maybe I'll just I should write strictly, because I also put it here. Okay. But I already know that this thing here is less than A. Right. So, and I also know, in fact, I know more than this. I know that this thing here is less or equal to A little n, as long as little n is bigger than capital A. That was just because the sequence was increasing. And all of them is smaller than this upper bound. So now you see that, so here you have A, all the elements AN lie to the left. And if you're looking at just the one from A capital N outwards, then here you have A minus epsilon, and then they lie between this one here and that. In particular, they lie to the right of this and to the left of that. So this means that they're squeezed in this little interval. And this, so this difference here, this difference from here to here, is certainly bounded by the distance to here, which was epsilon. Right? So this proves that this thing here is less than epsilon. Okay. And with obvious modification, the proof of that if you take, so this was an increasing sequence, the proof that if you have a decreasing sequence that is bounded, right, that the limit of that is the inf, the proof with obvious changes is the same. Okay. So now let's come back to square root of 2, right? And so we have this idea that square root of 2, in a way, to just get an idea about how large it is, you think about it as, you think about it as 1 and then a number of digits afterwards, right? That's a kind of approximation. So let's try to make this more precise.